welcome back. The topic of this video is the creation of photon and electron beams by linear accelerators, or as you'll often hear them called, linacs for short. I'm going to start, before I describe how these beams are produced, I'm going to start with a little motivation as to why you need such a complicated machine like a linear accelerator, why you can't just use an X-ray tube. And so let me go over that, and then I'm going to show how the beams are actually produced. Here we go.
Here I'm showing percent depth dose data for beams at 3 different energies. The first 2 are from X-ray tubes. The blue is a diagnostic X-ray tube, and the red is an orthovoltage tube that's used for treatment, and those go up to 500 kVp. The green is a megavoltage photon beam. Now, one thing you'll notice in these curves is that the red and the blue curve have a very high dose at superficial depths. And sometimes I think these percent depth dose curves can be a little bit hard to understand because it's normalized to the dose at the 100% at the maximum dose. So here I'm replotting these. And what I've done here is take the 3 beams and adjust them so that the dose at a depth of 10 centimeters is the same for all 3 beams. And you'll see that when I do that, the superficial dose is very high for the kilovoltage beams, the red and the blue. So it's really the megavoltage beam at high energies that gives you that low superficial dose, the skin sparing, which we talked about in previous videos. So that's the key advantage of a megavoltage beam. And now the problem is, how do you produce such a beam? Well, let's look at that. Well, if you're a simple person like me, you might just go back to this picture of the X-ray tube and remember that the voltage across these 2 electrodes, the cathode and the anode, accelerates an electron and produces a photon. As you increase this voltage, you increase the energy of the electron, and so the energy of the photon coming out. So why don't I just increase this voltage until I get up to the megavoltage MeV range? Well, you can't do that because the problem is if you go too high in the voltage, then this gap between the 2 electrodes will start to spark and break down, and you won't get the acceleration of these electrons. So you have to develop some other scheme, and so that's where a linear accelerator comes in, or a linac. So the basic concept in a linac is that you give up on these static fields and instead rely on time-varying fields or voltages. Let me show you how that works. So here you'll see these little red dots. These are bunches of electrons which are being accelerated through the linac. And they go through the center tube. The center tube is called the waveguide in the linac. And you'll see it's broken up into sections, and there are different voltages applied between these different sections, and these voltages vary with time. And then each time there's a voltage between the 2 cavities, that creates an electric field between those 2 cavities. That's a symbol E that you see there. And that field will accelerate the electron in the gap. So now let me slow this down and walk you through it a little bit closer. So I'm going to freeze this for a minute. So let's study this. So look at this electron here. It's experiencing an electron field, which causes it to accelerate. And also this electron over here has that. And you'll see that the field is on between these 2 cavities just when the 2 electrons reach that gap. And so the timing is everything in these systems. Now I'm going to speed it up again. And as I do, watch this electron. It goes through, it's going through. Okay, now it reaches the next gap, and right when it reaches that, the field is on between that gap again. So again, it gets another kick down the tube. And this way it's accelerated on its way down the tube. That's how these systems work, and they accelerate electrons to very high energies. The key to this is the voltage that's varying over time, because oscillating, and it's varying very quickly. As we'll see in a minute, these frequencies are in the radio frequency range, and often the voltages are drawn as waves to represent the radio frequency oscillation. Here's a picture of a cross-section of an actual waveguide. You can see it's made of copper, which is highly conductive, and you'll see the cavities that we just talked about, and the electron goes down through the middle. Here's a wave. Okay, I'm going to pull that down, and you'll see here, I don't know if you can see this, but it fits. The wavelength fits. One wavelength is exactly one cavity. And the wave goes through the waveguide like that. The RF wave goes through. That's called a traveling waveguide design. It's also possible to have it just oscillate in here, and the wave is kind of set up like a wave on a string. It's a standing wave accelerator. Those are two different designs. Different vendors use different designs for this, traveling or standing wave, and there's different advantages and disadvantages of each of these, but fundamentally they achieve the same goal of accelerating electrons down the tube. I'm just going to pull the wave down here, and then I'm going to go over to a cartoon of this waveguide. Now, this radio wave is actually an S-band wave. It's a microwave. It operates between 2 and 4 gigahertz. Remember, giga is 10 to the 9th. You can also have an X-band accelerator that operates between 8 and 12 gigahertz. So there, the wavelength is shorter, of course, so the accelerator can be more compact. And so those are the type of waveguides that are using compact systems like the Mobitron or Tomotherapy or CyberKnife or other machines where you need a very small accelerator. Now, these waves are all in the microwave range. So microwave we take as being here 300 megahertz to 300 gigahertz. And also, they're a type of radio frequency wave, RF wave, and the frequency range for that is 300 kilohertz to 300 gigahertz. So you'll see these terms sort of used interchangeably: microwave, RF, S-band, and so on. Let's go back here and look at the microwave. It moves with some speed v. Like I said, that's approximately the speed of sound, but it's a little bit, or the speed of light, but it's a little bit less than the speed of light, c. And the reason is because the phase velocity moves slower because of these little disks that are placed in between. So it's not moving in free space like a regular electromagnetic radiation. It moves a little bit slower. Second of all, the thing you'll notice here are these little sort of things on the side, these side cavities, they're called. And those allow a node to be placed in that cavity, and basically it acts to make the accelerating structure more compact and easier to engineer. So we're going to need to get the RF, the microwaves, into the waveguide in some way. So there's a whole subsystem that does that, and I'm going to go through that. So it starts here with the klystron or the magnetron that makes the RF waves. So it's one or the other. You can't have both. So let's go first over what the klystron is. Klystron is an amplifier. It's high power. It takes an input from watts and converts it into a microwave that comes out at megawatts. So it's large, bulky, expensive. It sits in an oil bath. It can't rotate with the gantry. So the alternative to the klystron is the magnetron. It's smaller and it's a microwave generator. Let's look at how it works. So you have a cathode here and an anode, which is a copper block. The cathode is heated and electrons boil off the cathode. They accelerate towards the anode because there's a potential difference of 4 keV. At the same time, there's a magnetic field here, a B field. So the electron, instead of coming off the cathode and going in a straight line, it curves around because there's a force on it from the magnetic field. As it curves around, it emits microwave radiation. Now let's go back here and look at how the microwaves get into the waveguide. They don't go straight, they actually go through this thing. This is called the circulator. It controls where the RF goes. It goes into the waveguide, and then as it reflects out, it comes back counterclockwise, or clockwise here, through the circulator. And then it can go into a couple different ways. So it can go into the automatic frequency control system. That's sort of a feedback loop that controls the frequency in the klystron. Or it can get dumped into here, and or it can get dumped into here into this load, sort of water load. What I'm drawing here is the standing waveguide. In a traveling waveguide, the circuits for the radio frequencies are a little different. So there's another little bit of detail I'd like to describe here, which is about the vacuum system. So normally everything is at a very low vacuum, and that is to prevent sparking or arcing. When you're dealing with high voltages, if there's even a little bit of gas in the chamber, it can act to catalyze an arc. So these systems need to be at very low vacuums. However, that's a little difficult and expensive to maintain. So there's one exception here, which is this region here. And this is actually filled with a gas, SF6, sulfur hexafluorine. This sulfur hexafluorine is at high pressure. It prevents arcing. You should also note it's toxic, though. There's a little window here, a glass window that separates the waveguide, and a ceramic window that separates off the magnetron or klystron, which are at low pressure. So now you've got this system that's filled with microwaves. They're going to accelerate this electron through the waveguide. And then in the end, that's going to come out at the end, and that's going to produce your output for the patient. So we need to introduce this electron into the system along with the microwaves. So this starts over here on the left-hand side with something we call the electron gun, the gun that introduces bunches of electrons. And it's important that they travel in bunches, and each bunch goes through here. I'm not going to talk much about the design of the electron gun, but it's basically like a cathode where the electrons boil off. Then a key thing here is the pulse network. So it starts at the modulator. That gives pulses out into the klystron or magnetron, and then also at the same time into the electron gun. So these two systems are coordinated, so they sync together. The key component of the modulator is the switch that turns things on and off very quickly, because it has a DC pulse and it gives an output of very fast pulses. And the switch in the modulator was a thyrotron. That's a gas chamber. It switches on and off. But in modern system, solid state components are used, like the IGBT or a FET, field effect transistor. So as I said, there's pulses for electrons. They don't come out in a steady stream. So let's look at that. Here's the pulse train. This is time, and then looking at the pulses. So I might be plotting the current, for example. Each of these pulses is very short, 2 to 4 microseconds in duration, while the time between pulses is much longer. So it might be like 5 milliseconds, let's say. And then these pulses of electrons are fed through. So important thing here is probably the current. So we look at the current in the peak, and the current in the peak is going to determine the output of the machine and also the pulse rate, those two things together. So the current in the pulse itself will be either 1 milliamp, let's say, for electron mode, or up to 100 milliamp for photon mode. So very high power in this very short pulse. So now we're going to go back here and look at the high energy electron beam coming out of the waveguide. Problem is the patient is down here, right? You want this beam to somehow get down to the patient for treatment. So that is something we need to accomplish. It's accomplished with this, which is called the bending magnet. That is going to supply a magnetic field like this into the page. And of course, you remember that with a B field, the electron traveling this direction will experience some force, and that will cause the electron to curve, go in curved. And so that's how you can change the direction of the beam. It's kind of like the magnetron. So the electron comes out and comes down here and bends down towards the patient. I'm going to draw it like this for now. We'll get into the design in a minute. So now you have an electron beam coming down. What you really sometimes want is a photon beam to treat the patient. So let me just back up a minute and explain that, how the photon beam is created. So you have here something which is called the target. It's made of tungsten. Hits that and makes bremsstrahlung photons that come off in various directions. So let's go back and look at the bending magnet for a minute now. So we have these electrons coming down through the 90-degree bend. And let's look at the spectrum of electrons coming out. So here I'm going to plot the number of electrons on the vertical versus the energy. That's the spectrum. Now these electrons don't come out of the waveguide all at one specific energy. No, there's some distribution of energy. Some are a little bit slower, some are a little bit faster. So I'll draw kind of like a peaky Gaussian here. So here are the faster electrons, and here are the slightly slower electrons in black. So let's look at what those look like. The faster one, the red one, is going to bend with a larger radius. Okay, it's moving faster. The radius of curvature is larger. It experiences the same force, but it takes like a longer time to get bent around. The slower one is the opposite. It gets bent in a smaller radius. So they land at different places on the target, and that's bad actually, because then you're going to have a large spot size. It's going to make a big penumbra, and as you'll see later, that has negative consequences. So we need to have a different design. So I'm going to zoom in here and look at a different design for the magnet. So in this design, the electron comes in just like before, but then it's actually bent around through a bigger angle. So it goes through 270-degree bend, comes back down around, and then down to the target, hits it at that spot. So this is an electron with some mean energy at the peak. Let's look at what happens to the faster electron, the red one. So it comes around, it actually gets bent around this like the first one, but it's a larger radius because it's going faster, and then it comes down to the target. Now why does it bend around like that in the larger radius? The reason is that actually the B field, the magnetic field, increases as you go out away from the center. And so it gets bent around more at the higher energy ones, get bent around more, and they come to the same spot. I'm not going to explain in detail this B field increase, but it's a design of the magnet. Now you can imagine what happens to the slower electron. It comes in and it goes through a smaller bending radius like this, and again is focused down on the same exact spot in the target. So this little cartoon illustrates that. So they're all coming to the same spot. That is called achromatic bending. That's a term that's borrowed from the optical industry, achromatic meaning colorless or energy independent. No matter what the energy, they all get bent to the same spot. So there are different types of magnet systems, and let me go over a different one just for completeness. This is called a slalom magnet, as you'll see in a minute. So the geometry is slightly different. You've got two magnet sectors here. These are 45 degrees, and then a third sector which bends the beam through 112.5 degrees. This is the beam path. If the energy is slightly higher, it'll get bent more, again because of these gradients of the magnetic field. And so again, focused onto the same spot. If the low energy beam goes like this, and again going to the same spot, so it's achromatic. One of the advantages of this design is this smaller height in this direction, so that can make the head of the linac slightly more compact. So now I'd like to focus in on this thing here, which is the target. That's where the electrons are converted into photons through the Bremsstrahlung process. Let's look at the physics of that. So to understand this, let's look at this famous plot, which shows the radiative and collisional stopping power in the target. If you need to review this, go back and look at video 7.1 and 7.2. Here's the radiative stopping power, and here's the collisional stopping power. You notice they're quite different. Now we're up at higher energies for the therapy purposes. So let's say we're up here at 6 MeV. And you can see that the rate of collisional loss and the rate of radiative loss is pretty similar, meaning that the target is pretty efficient at producing these Bremsstrahlung photons and through the radiative loss mechanism. Remember also that the photons are relatively forward directed. So if this is the target and this is the electron beam coming in, it hits the target and it produces photons. In a diagnostic tube, these came off at 90-degree angles like this. In a therapy tube, they're more forward directed, so they come off this way. That's going to be important later. Let's look at what one of these looks like in real life. This is the target, and you can see here the silver bit, which is the target piece, and it's in a copper structure that cools it. And then you can see the tubes that go into it. These are water tubes that carry water for cooling the target off, because so much heat is generated because of the collisional losses.
Now I'd like to take a minute to talk about the energy of the beam. The energy is determined not by the number of electrons coming out of the flux or anything. It's by the actual energy of the electron as it emerges from the waveguide, the speed coming out. So you can control that. There's a thing here called an E-switch, the energy switch. There are different designs, mechanical designs, electrical designs, but they sort of decouple various parts of the waveguide. So you can change the energy. So you might run in, let's say, 6 MV mode. That's how you call it, 6 MV. That's just the nomenclature. That would correspond to a maximum energy of about 6 MeV. Or you could run in a high energy mode, 18 MV, let's say. And again, that would be something where the highest energy is approximately 18 MeV, the highest energy photon coming out, 18 MeV. So there you go. Those are the basics of beam production in a linear accelerator. What I've tried to do here is assemble information from a lot of different sources to make it a practical kind of reference guide. But of course, these are complex machines and there's much more you can learn. So I'm going to leave you with this reference reading list. You can dig in and read a little more. The green book in particular is one that I like. And then in the next video, we're going to go into the practical aspects of the beam production. So what happens after the target, which is up till now we talked about just to the target, but after that you collimate the beam and you turn it into something that is usable in a patient. That's actually a very complicated topic, and I think you need to understand it in detail. So I've made a whole video just about that particular topic and about Linacs. So we'll see you next time.